PreCalc. We're watching this on Thursday, preparing for Friday's class, so that's 4:20. And we're going to spend the day doing one probability problem. Come in and work on your previous probability assignments, and when you finish, begin this one. So this one is coming from the book on page 713, where it says, a coin of diameter d is dropped onto a paper that contains a grid of squares, not d units on a side, and you can see the picture. Find the probability that the coin covers a vertex of one of the squares on the grid, and perform the experiment 100 times and use the results to approximate pi. So I bet pi shows up in the probability somewhere, so that way we can use it to approximate pi. Alright, so let's make some sense of this. You're going to have to go into the teacher's room in one of those little cubby holes where the paper is, find a bunch of scrap paper, and that is plain on one side. I think it's in the bottom left cubby. Just grab one of those for each person, and we're all going to do this. So we are going to construct a grid that will cover this whole side of the paper. So that will take a while. So I recommend you just start in the center of the paper and draw the penny, or not draw the penny, but mark the sides of the penny as close to the penny as you can. The more accurate, the better your results. Alright, so from this four sides, I'm going to create a grid, keeping this very straight. And I'm going to go up and down my whole paper. And I'm not showing you a portion. You're going to do the whole paper, and I'm going to just do one, or maybe two. Alright, so that penny should fit exactly into that square, touching the lines on each side of the penny. So therefore, to keep going, I need this one. And I'm running out of space with my camera legs in the way. Alright, so alright, and so on. So I'm going to create a grid, and you see I'm doing it quickly, and this looks a little crooked. Penny fits in there. I don't know, it might be alright. But anyway, you're going to create a grid that is very accurate, very straight, and will cover your whole paper. So the whole paper will have a grid on it, like this problem indicates. The picture of this problem indicates. Alright, so I'm going to talk about just one of these places. So the problem says to find the probability that the coin covers a vertex. So let's talk about that. The probability that the coin covers a vertex. I'm going to take this penny and put it in such a way so that the center of the penny is exactly on a vertex. Now, to meet this requirement, it wouldn't have to be centered. It could be like this. This coin still covers a vertex. Again, these are the vertices, these four corners. So when I drop the penny, I'm looking for the probability that it'll cover a vertex. Now, it could be any vertex on the whole one, but I'm going to study just one vertex. So this vertex, just for this drop, I'm going to consider when the center of the penny is right on a vertex. I'm going to try to draw that. I'll probably be a little bit off, but we can get the idea. Alright, so let's pretend that this vertex is in the center of that circle that I drew. And you can draw this roughly in your comp book now, so that when you look at it later, you can remember what to do. So this is one penny high, and it is 1 penny wide. All right, so to come up with this probability, let's just look at one vertex. So obviously, if the center of the penny falls on the vertex is covered. What if the center of the penny falls here? So can you see, if that's where the center of the penny is, it still covers the vertex. What about if it falls here? Trying to line it up to convince you. It just barely covers the vertex. But what I'm trying to establish, that if the center of the penny falls anywhere within this circle, within, then, like say I'm right there. If the center of the penny is right there, it still covers the vertex. So that idea is going to help me come up with the probability. So the probability that the coin covers a vertex is going to be related to this area around the vertex, and it's going to be also related to I want to show that the area in which the coin, I'm going to make this probability, the area in which the coin may fall like a probability is, I'm going to look at the area when it covers a vertex. I'm going to look at all that area where the coin may fall, the darkened area, divided by the total area. Alright, so since I'm studying the area around one vertex, I am going to consider the total area to be this. And then if I did that here, here, and here, I would be constructing squares and circles around each vertex. But I'm only going to study one, and then I can multiply my results for as many vertices there are. So let's take the area in which the coin may fall for one vertex and divide it by the total area around that vertex. So if the coin falls so that the center is in here, then it will not cover the vertex. So let's see if that's true. So here's the center. I'm going to try to line it up right on top of that. And you can see that the vertex is not covered. So we can find the probability by taking the area in which the coin may fall around this vertex divided by the total area around that vertex. So the area around, so this has a radius of r, whatever the penny's radius is. So we have area in which the coin may fall. It's a circle. So we have pi r squared divided by, what's the area of this square around the circle? Well, how long and what are the two dimensions, width and length of the square? So r is right here. The radius of the penny, I can drop it down here and see that this is r and this is also r. So one side of our square is 2r. The other side, being a square, is 2r. 2r times 2r is 4r squared. So we end up with pi over 4 around this vertex. But how many vertices are we going to have in our whole paper? I'm not sure, but we'll say there's n number. So we can multiply this area, pi r squared, by the number of vertices, and then we're going to build an area around each of them. How many? N of those. So the n's will cancel, and we end up with pi over 4. Even though we're looking at one vertex, the probability for all the whole paper is still pi over 4. So as we suspected, pi showed up in our probability. So the probability that a coin covers a vertex is pi over 4. Alright, So having established that, we're going to make a grid and we're going to drop the coin 100 times. Each person does this. And we're going to count the number of times the coin covers a vertex, any vertex on the whole paper. If your coin pops off of the paper, which it does, don't count that one. So we'll count that, we'll drop the penny 100 times onto the paper. The number of times the coin covers a vertex, so you're going to keep count, divided by the total number of drops will give you a probability, and that should approximate pi over 4. So pi over 4 is what we calculated, and your number should be pi over 4. Suppose you dropped 100 drops and 75 of them, 75 out of 100 is what you found out. So because that's approximating pi over 4, should be, the more you do it, the closer it should get to pi over 4. Take your number and multiply it by 4. And just like this number, when you multiply it by 4, you get pi. Your number multiplied by 4 is your own personal approximation of pi. So if I did this rough example, 4 goes into 100, 25 times 75 divided by 25, I got my approximation is 3. So this I just made up. So we're going to see if this works. We're going to see how close we can get to pi with 100 drops, recording the number of times the coin covers a vertex divided by the total number of drops, and only counting the ones that actually land on your paper. These coins tend to pop around. So we will conduct this experiment. When you get this number, multiply it by 4 and see how close it is to pi. And the number for pi is, see what some of the extra digits are. See, my calculator is fighting me. All right, 3.14159, and it goes on. Never ends and never repeats. So you can go ahead and conduct that experiment on Friday after you finish your probability problems. So let me know how it goes and what your approximations turn out to be. And I will be available by text if you need to ask me additional questions. So I will leave that information with one of you. Okay, that's it for now. I hope that this experiment finds your approximation of pi to be quite satisfying. Carry on, class. Carry on.